Okay, so we're going to start this lesson here. Last chapter, last chapter, which was 11.1, we talked about Alfred Wegener and his idea of continental drift, that the continents were moving along. And that was the first video I ever made, so congratulations to Mr. Staroscik, right? Okay, hold your thought. But I'm going to try to make this one a little shorter because sometimes I get a little winded. So this chapter, this is just the next chapter in the book. It's called 11.2, and it is called Seafloor spreading. So I kind of left you with a hanger on the last video where I said that Wegener's ideas weren't really widely accepted, and most of it is because, like it says here, that he didn't really have any evidence to prove his ideas. He just said them, but he didn't really kind of explain why this is what he was seeing. So it took a while, and it took about till the 1950s, and it took about until the 1950s for Wegener's idea of continental drift to be accepted. And this is because of this evidence. This is why it happens. So we have all these scientists saying, Wegener, no, you don't know what you're talking about. Yeah, maybe this is true, but you can't prove it. Well, they finally were able to kind of prove why continents are drifting. So they can kind of really show why these continents are drifting. And it's because of the 1950s. If it wasn't for World War II, this might have been delayed longer. But World War II had some new technology developed, right? And this was the technology called radar. And radar was particularly important. Radar was developed in the war by the British. Radar was developed in World War II to keep track of enemy movements. And it was especially needed in the ocean, because submarines are floating around the ocean. If you're a big battleship or a destroyer or something, or maybe another submarine, cruiser, an aircraft carrier, something like that, you got to know if there's anybody floating around underneath of you. So we had these radars developed. Okay, especially important for naval, we'll call it naval warfare. Not with your belly button, but like naval warfare as in ships. So because we had this naval warfare, we had radar developed, we started to be able to kind of map the ocean floor. And so the way radar works, for those of you who don't know how radar works, radar kind of works where if I'm a boat here, so this is the ocean, and on the ocean I have this boat, and for lack of just, I'm a bad trawler, I'm going to make it a sailboat. Most sailboats do not come equipped with sonar, okay, or radar. We call it sonar if it's in the ocean. Most sailboats, actually no sailboats do. Actually, some of the new ones might. But anyway, I'm a sailboat, and I'm floating around the top of the ocean. This is the bottom of the ocean, which I know nothing about. Okay, I'm going to actually make it a little bigger. I know nothing about the bottom of the ocean. Okay, but I assume it's pretty flat and there's some things on it. Well, with the advent of radar, you were obviously looking for, if I'm a boat, I'm looking for a submarine down here that might come out and try to shoot me. So I'm looking for that. So I have this thing called radar, which is basically a pulse. It's a sound that I shoot out of my boat, and these sort of waves get shot out, and when they hit something, they get deflected back. So these get deflected back. If there's a submarine here, they're going to get deflected back. And based on the amount of time it takes for these to get sent back, you can kind of calculate what's in the air, so or what's in the water. So if this takes a little bit of time to get bounced back, you would make the assumption that there's something floating underneath of you, and you're either going to get a torpedo pretty soon, or there's a giant whale. But you don't really know. So this was very important in the war, to be able to tell where submarines were or other things like that. But afterwards, it became very important in science, because if you're a boat now, you can shoot your radar down to the surface of the ocean, and you can kind of get a pretty good idea how the ocean looks. Because if there's any sort of like ridge or mountain or anything underneath the ocean, you're going to get a signal on your radar. Okay, so this was huge. This was huge stuff. This was great because when they started to map the ocean floor, they found out that contrary to popular let's not use that color. Contrary to popular belief, the ocean floor was not flat. It was actually very jagged and rigid and things like that. So that was a brand new thought. Nobody was thinking that the ocean actually looked like that. And on Google Earth, in some places, I'm fairly certain you can go into the water, and we may be able to see what the ocean floor looks like. And here it seems pretty flat and stuff, but there's definitely some ridges and things like that that you can see floating around here. So we have this sort of not flat ocean, which is a great observation. And what they particularly noticed with this not flat ocean, with this new technology, is, there we go, is that there was this giant ridge right in the middle of the ocean. In fact, every time they crossed in between North America and Europe, they will be able to pick up this giant ridge. And this ridge is so big, you can see it from Google Earth. Okay, you can see this ridge. I'll try to go slow so it picks up. But you can see this ridge, okay, that goes the length of the ocean. And if we zoom in on that and actually look at it, we find that not only is it a ridge of mountains and things like that, it is, well, this isn't a very good spot. Yeah, there's some good stuff. It's actually a volcanic range. Okay, so not only do we have really tall mountains under the ocean, we actually have volcanoes underneath the ocean. So you kind of think about it like that. These ridges now are actually spewing out hot lava almost constantly. Okay, so this mid-Atlantic ridge is the one we're going to call this here in North America, or excuse me, in the Atlantic Ocean. This mid-Atlantic ridge, which you can very, very clearly see from outer space. Well, maybe that's why I couldn't see it. Okay, which you can very, very clearly see from outer space, right there. All of this stuff right here, right? That was there, and there was lava spewing out of it, the whole length of it. So this was incredibly interesting to people. So the scientists started to say, okay, well, because of this new radar showed that the ocean surface, the bottom. How about this? How about the bottom of the ocean was not flat? Okay, and it particularly showed there was a volcanic mountain range in the middle of the Atlantic Ocean. Today we call that, scientists are super creative about life, guys. Today we call that the Mid-Atlantic Ridge. That's what we call it today, and it's a very huge part in this course. We're going to talk about it a lot. Okay, the Mid-Atlantic Ridge. Okay, so we find this Mid-Atlantic Ridge, and now all of a sudden things are like, holy smokes, because maybe Alfred Wegener was right. Maybe there's lava coming up from the ocean, and it's pushing the seafloor apart, which would also end up pushing the continents apart. Okay, so we had this guy named Harry Hess. You don't need to know who that is, but he proposed this idea of seafloor spreading. Okay, and in seafloor spreading, hot magma comes up through the ocean crust and pushes the crust apart. And this happens very slowly. It happens like extremely slowly, not fast at all. You sort of have, if this is our ocean, and you got your surface right here, right? And you got these little tiny volcanoes that are pushing up. And what you're having is this magma kind of shooting up all the time. And what that does to the surface is it starts to push this out because the magma comes up and it's cold, right? So it's going to cool. The magma cools and it starts to kind of push the rock out. It pushes the rock out. And I think this is a good example of it too. We got this magma cooling and pushing the rock out. Okay, so this seafloor spreading. How about this right here? Okay, you can see this really good. The magma's coming up. It's pushing the ocean crust apart, and in doing so, pushes the continents apart. So this is an absolute definite thing that this guy named Harry Hess figured out, and he said, look, this Alfred Wegener guy, he wasn't crazy after all. There is actually a mid-ocean ridge, and there is actually this pushing apart happening. And the seafloor is a great place to look at this. So these continents are moving apart. It's because the seafloor is being pushed apart. Okay? So we're going to talk about a few evidences of this happening. So we got evidence of seafloor spreading. Is what we're going to call this. Evidence of seafloor spreading. And the first evidence, you might as well be done with this one too. It's a great evidence. Is age evidence. And they can date rocks. You can't take them out for dinner, but you can figure out how old they are. And the way you figure out how old rocks are is you can do some radioactive stuff, figure out how many atoms are there, and you can say for certain that this rock is somewhere between 60 million years old and 65 million years old. Okay? I know it's a big range, but in geology time, it's not that big of a range. So what they did when they started to test the age of ocean rocks, they found out that no rocks on the ocean floor are older, that's how you spell older than 180 million years. So nothing on the ocean floor is older than 180 million years. This is crazy because you can go anywhere on the continents and find rocks that are much, much older than 180 years. But nowhere in the ocean can you find anything that's older than 180 million years. So there must be something going on here where this old rock is kind of decayed. And you can see it right here. Look what happens. We have the ocean crust being pushed up. These rocks get pushed out, and eventually they end up going back into the ground again. So the oldest rocks in the ocean crust then would have to be these ones, right? The oldest rocks then in the ocean crust would be these rocks right here. All these old rocks get recycled back down and they become magma again. So the newest rocks, when they started to date these, again, they didn't take them out for dinner, but they started to date these, they found that these rocks right here were the newest. They were the youngest rock. They weren't very young, they weren't very old at all. While these rocks over here were old. Okay? So that's great evidence. You can date these rocks, you can figure out which one's oldest, which one's newest, and this is kind of the sort of thing they started to discover. Great discovery, okay? So you can go anywhere on the continents. Like I have a rock in my rock collection that's 400 million years old. That's twice as old as this. I have another rock in my rock collection that's 1 billion years old. Okay, I have a rock in my rock collection that's 3 billion years old. That's a lot older than anything on the ocean crust because that gets recycled. It goes back into the crust, it melts, okay? So that was a big piece of evidence. It's age evidence. Okay, the other evidence, and this is there's two of them. The other evidence is magnetic clues. So this is super interesting to me, and magnetic clues show an alternating pattern of magnetic fields in the ocean crust. Okay, so let me kind of explain what's going on here. We in the ocean, or in the Earth. Oh, let's talk about the Earth first. Okay, so the Earth, like this is Earth, and it has a North Pole and it has a South Pole. And that's how it is right now. These poles are kind of determined by the stuff that's kind of floating around in the middle of the Earth. We don't even talk about it, but we do need to know that every so often, and it's actually pretty regularly. I'm trying to see if I can find how regularly it is. I think it's every 30,000 years, but don't quote me on that because you won't need to know it for the test either. But we'll say it's about every 30 million years or 30,000 years. About that often, the poles flip. So the North Pole will go to where the South Pole is, and then what we get is Earth again. But now the South Pole is pointed up, and the North Pole is pointed down. This happens quite a bit. Like I said, every 30,000 years. And I don't know if it's 30,000 years, but it's a very periodic thing. It's very easy to tell when it's going to happen again. So we have this flip of these poles. Well, rocks, a lot of rocks are magnetic, okay? So a lot of rocks have this magnetic polarity, we'll call them, because they have iron in them. And iron is attracted to magnets, okay? So they're not very attracted, but let's just say, I don't like that. Let's say that I'm a new rock and I'm in magma, so it's liquid, I can move around, right? Well, I'm going to want to point myself, say, north. So if I come out of the ground in the surface of the crust and I'm a new rock, I'm going to point myself towards the north, okay? If this is north. And I'm gonna do that because I'm liquid and I can move and I like to be looking north, okay? So that's what happens. I'm orienting myself. I'm a piece of iron filing and I'm orienting myself to the north. But since these poles flip, what they've found is that every so often you can go to the Earth's crust and find distinct patterns of the rocks being pointed the exact opposite direction. And they're alternating bands. So we must assume then that during this period right here, north must have been down. So we had a flip of the pole where north was down, right? So this happens over and over again. I had my hand on the keyboard. So this happens over and over again, and now we're going to assume that north is here. North is here, north is here, if the arrows are pointed up. Okay? These alternating bands. Okay? Sort of looks like this. These, this is reversed magnetic polarity is what it's saying. So it's saying north is down this way, and these pink bands, north is up. Okay? And a better way to look at it, here we go. You see the positive and the negative. So that way, this is huge evidence. And this one even tells you how old the crust is. So based off of when the rotation happened, you can see the polarity of it. Okay, polarity meaning magnetic field of it. So the magnetic field is pointed up, the magnetic field is pointed down. And we get these alternating patterns in the ocean's crust. Okay, centered around this. So I want to make sure we're cool with this. I hope we understand that these are pairs. So like if I call this a pair, I'm going to say this is A and this is A, this is B, this is B, this is C, and this is C. Okay, so they're kind of moving out because the motion again is outwards like that. Okay, so this is again a cool idea. Seafloor spreading has to deal. This finally proved Alfred Wegener right. This was the kingpin. This was it. Okay, so that's it for the notes today, and have a wonderful, wonderful day.